What if our vast network of roads could do more than just carry cars? The idea of solar roads is simple and deeply appealing. Replace dark asphalt with smart electricity generating surfaces. This could power our world without taking up new land, turning existing infrastructure into a source of green power. It sounds like a perfect solution, but the reality is often far more complicated than the dream. The central question we need to address is whether solar roads are a viable part of our future energy mix or merely an expensive distraction. Can these systems genuinely produce a meaningful amount of electricity, or are they a novelty with limited practical application? This essay will provide a sober, data-driven examination of solar roadways. We will move beyond the glossy marketing materials and the viral social media posts to look at the actual performance of these projects. The goal is not to dismiss the idea outright. We aim for a fair, rigorous assessment based on evidence from years of pilot projects and real-world trials around the globe. To do this, we'll break the topic into core components. First, how solar roads are supposed to work. Different technologies, panels laid on top of pavement, fully integrated glass and cell modules, how they convert sunlight into electricity, and how they connect to the power grid. Then, the numbers. Energy produced per square meter, efficiency versus traditional panels on a roof and in a field. Costs, installation maintenance. Next, case studies, celebrated successes, quiet failures. France, the Netherlands, China, United States. Lessons, what works, what doesn't, and why. Practical issues, durability against traffic, skid resistance, and other safety concerns. Keeping surfaces clean enough to generate effectively. These practical experiences give the best insight into true potential. Finally, weigh benefits and risks compared to alternatives. Alternatives, carports, highway canopies, rooftop installations. By the end, you'll have a balanced understanding of solar road technology. Decide revolutionary path forward or a dead end on our journey to sustainability. Let's begin with the fundamentals. At its core, a solar road works on the same fundamental principle as any other solar panel. It uses a material that converts sunlight into electricity. This is the photovoltaic effect. The key components are solar cells. They are typically made from silicon. When photons from the sun strike these cells, they knock electrons loose. That flow of electrons is electric current. So the first step is a surface with photovoltaic cells. The goal, capture sun energy hitting the road every day. But a road is not a rooftop. It must do more than generate power. A solar road panel is a multi-layered sandwich. Top layer transparent so sunlight reaches the cells. Top layer also extremely strong and durable. It must withstand weight from a small car and from a fully loaded 18-wheeler truck. It also needs to provide grip or traction for safe stops, including wet conditions and icy conditions. Beneath the top layer is the array of solar cells, the energy converters. This layer is protected from traffic and weather. Under that is a layer housing electronics. This electronics layer enables features beyond power. LED lights for glowing road markings, heating elements to melt snow and ice. All layers are sealed into a single robust module. Each module is engineered to connect with its neighbors. Roads are many panels laid side by side. They link up to collect electricity. Each panel includes wiring and connectors for power and data. Together, they form a connected grid, combining small outputs into usable electricity. Think of it like a big Lego set. Each piece builds structure and generates power. Once solar road panels generate direct current or DC, the journey is just beginning. Our homes and the grid run on alternating current or AC, so the raw DC power must be converted by a device called an inverter. This AC power can then be used to power the road's own smart features or be fed into the main electrical grid. To provide power at night, excess energy can be stored in large batteries. Not all solar roads are created equal. Engineers have experimented with several different designs to try and solve the challenges of combining solar panels with pavement. The most famous approach, popularized by companies like Solar Roadways in the USA, involves creating heavy-duty modular glass panels. These are typically hexagonal or square tiles. They contain solar cells, LEDs, heating elements. The top surface is made of thick tempered glass, textured to provide skid resistance. These modules are designed to completely replace the asphalt surface, fitting together to form the new road. Another method is to embed existing solar panel technologies into the road surface. This approach, seen in projects like Francis Watt Way, uses thin but durable solar modules essentially glued on top of the existing asphalt. The panels are only a few millimeters thick and are coated with a protective layer of resins and polymers to withstand traffic. This makes installation much faster and less disruptive than ripping up the whole road. The idea is to retrofit existing roads rather than building new ones from scratch. This method avoids the major costs and civil engineering work associated with a full road replacement. A third, more experimental concept involves developing a new type of building material altogether, transparent concrete. This is a futuristic idea where the road surface itself is made of a special concrete that can transmit lights. Optical fibers are embedded within the concrete mix, allowing sunlight to pass through the pavement to solar cells protected underneath. This approach could theoretically offer the durability of traditional concrete while still allowing for solar energy generation. However, this technology is still very much in the early research and development stage and is a long way from being commercially viable or ready for large-scale deployment on public roads. Each of these designs comes with its own set of trade-offs. The heavy-duty glass panels are strong but expensive. Their glass surface presents challenges for traction and glare. The stick-on panels are cheaper and easier to install, but their durability under constant heavy traffic is a major concern. The thin layers can wear down or peel off. The transparent concrete concept is fascinating but remains largely theoretical for now. Understanding these different approaches is key to evaluating the results from various pilot projects, as the success or failure of a project often depends heavily on the specific technology that was used. When we talk about performance, the first and most important question is how much electricity do solar roads actually generate? The promise is vast, but pilot project data tells a more modest story. Let's look at the numbers. Typical rooftop solar under good conditions, around 150 to 200 watts per square meter. Solar road yields have been consistently lower. For example, Francis Watt Way reported about 70 kilowatt hours per square meter per year. In a sunny location, a standard rooftop system would produce closer to 200 kilowatt hours per square meter per year. So solar roads often produce less than half the energy of conventional solar on the same area. We'll examine the reasons next. Bottom line output is the critical starting point. If solar roads are less than 50% as productive as rooftops, they need extraordinary other benefits to justify themselves. Trials often show 50 to 100 kilowatt hours per square meter per year. Results vary with location and technology. Let's put this into a practical context. Imagine a 1 kilometer stretch of a single lane about 3.5 meters wide. That gives a surface area of 3,500 square meters. At 100 kilowatt hours per square meter per year, that produces 350,000 kilowatt hours annually. That sounds like a lot, but the average American household uses about 10,700 kilowatt hours per year, so that entire kilometer would power roughly 33 homes. That's a far cry from powering entire cities. These figures frame the debate. Solar roads do produce power, but the quantity is the main issue. The output is not negligible, but it is not revolutionary. It's supplemental energy, not a replacement for power plants or large-scale solar farms. Acknowledging low energy density is the first step to a realistic conversation. It's not a magic solution, a niche technology with limited output. The low energy output of solar roads is not an accident or a sign of poor manufacturing. It is a direct result of fundamental design compromises when you try to turn a road into a solar panel. The biggest factor is the angle of the panels. Solar panels work best when tilted to face the sun directly. Solar farms are angled. Rooftop installations are angled, often at 30 to 45 degrees depending on latitude. A road must be flat. Flat panels get much less direct sunlight, especially in the morning and evening and throughout winter when the sun is lower. That orientation can cut energy capture by 40 to 50% versus an optimally tilted panel. Next, dirt, dust, debris. Rooftops and solar farms are relatively clean. Roads are filthy, covered in dust, mud, tire rubber, oil, and salt in winter. Even a thin layer of grime dramatically reduces light to the cells and slashes output. Rain helps, but constant traffic buildup means solar roads rarely run at clean state efficiency. Keeping them clean needs frequent, expensive street sweeping. Specialized equipment adds operational costs that rooftop panels don't have. Then shading. Roads are often shaded. Cars, trucks, buses block the sun as they drive. A single parked car can disable a whole section depending on wiring. Trees cast long shadows. Buildings cast long shadows. Rooftops are chosen for unobstructed sky access. Road location is set by transportation needs, not solar potential. Many roads sit where you wouldn't place a solar farm. Finally, the protective top layer reduces efficiency. Thick glass or polymer for traffic isn't as transparent as thin solar glass. It must be thick and textured for grip. Those properties scatter and reflect incoming sunlight before it reaches the cells. Every layer between sun and cell cuts final output. The flat angle, the constant dirt, the frequent shading, the less than perfectly clear top surface. It becomes obvious why real-world solar road performance is much lower than rooftop counterparts. For solar roads to make economic sense, their cost must be exceptionally low. Unfortunately, the opposite is true. The cost is astronomically high. While utility scale solar costs under $1 per watt, pilot solar roads have cost $100 to over $200 per watt. Even the more affordable projects are over 10 times the cost of rooftop solar. This is due to complex panels, extensive road work, and specialized maintenance, making the electricity they produce among the most expensive on Earth. With low energy output and high costs, the financial viability of solar roads comes down to the payback period. Even with optimistic estimates, a simple calculation shows it would take over 40 years to break even, far longer than the panel's expected lifespan. And this doesn't include maintenance costs. The payback period isn't just long, it could be infinite, making the project a permanent financial drain. We began by contrasting the seductive dream of solar roads with a reality check. The verdict is clear. Solar roads in their current form are a technological dead end. They produce little power at an astronomical cost and can't withstand traffic and weather. The lesson is to focus our resources on solutions that work today, accelerating rooftop solar, covering parking lots with solar carports, and using land alongside highways for efficient solar farms. While niche research may continue, paving our major highways with solar panels should be taken off the table. That is the real path to a sustainable future.